So I'm going to get started. Today's announcements are that the sapling chapter 18 is due 9 a.m. Wednesday. Also, I have the exam grades here for anyone who submitted them and still needs them back. After this morning, I'm going to parcel them back out to the TAs so you can just get them in recitation after that. You should be seeing a grade change online, though, if you ended up getting one. And then also, we have an exam review coming up this Sunday because the exam is the Tuesday right after that. So just like before, review session is going to be Sunday 2 to 4 in Math 100. So I'll put up more reminders on that. But basically, just bring whatever questions you want to go over. So it's worth your time to make sure that you do a bunch of review work before then so that you have good questions to ask or so that the questions that do get asked sort of make sense to you. Okay. Questions about any of those? All right, cool. So we are into chapter 19. The notes are posted and the sapling homework should be open. So I'm just going to pick up where I left off. We're looking at aldehydes and ketones in this chapter. And in this particular section, we're looking at reversible additions to carbonyls. Okay, so we looked at hydration last time, which is you take an aldehyde or a ketone, and you can use H3O plus, either acidic water conditions to make the gem diol, and these are reversible, so even though I draw it as a one-directional arrow because we're mostly focusing on like emphasizing the Ford reaction, it can go either way, and we're going to look at where the equilibrium lies a little bit today. So we saw acidic conditions in water, and we also saw basic conditions in water. Both of these do the same thing, make the gem diol reversibly. Okay, and then we also started looking at, so that's hydration. We also started looking at cyanohydrin formation. Where you take a carbonyl and you add some sort of cyanide source, so like Na plus C triple bond N minus and HCN, and you can reversibly add CN to the carbonyl instead of OH. Okay, so for this one, we're not actually going to cover it in acidic conditions. It really only works in basic or nucleophilic conditions. And that's mainly because like HCN, the conjugate acid that we're using here, is not actually strong enough to protonate the carbonyl to get the reaction started like H3O plus was. So basically, no pun intended, you need to have a base here to do this. So cyanide ion, C triple bond N, needs to be the thing that gets this reaction kicked off. Okay, so you can either set this up as NaCN with some extra HCN around. As a quick review on the mechanism here, mech is going to be C triple bond N is a good enough nucleophile that it just goes straight in for the attack, whether or not, or despite the fact that the carbonyl is not protonated. And then you get to here, which can then go take an H off of the conjugate acid of that nucleophile. To give you the cyanohydrin. Okay, so exactly the same mechanism, or analogously the same as base and water. It's just instead of an OH minus starting things off, you have a CN minus starting things off. Okay, so you can either set this up with like C triple bond N and HCN present, or you can more traditionally write this on the arrow as something that will create those conditions. So you're sort of generating one of the reagents in situ. So like a real common historical way of setting this up is this and then NaCN 1 equivalent, and then something that's going to make some HCN, but not so much that it's going to use up all of your CN minus. So like HCl, slightly less than 1 equivalent. People usually say like 0.9 equivs, but the exact amount is not too important, just so long as it's slightly under 1. And then these two things combine to make HCN and leave some CN minus, some cyanide left over to go start the attack. Okay, so it's really just different ways of writing the same reaction here, but you might see either one, so as long as you can recognize that's what's going on. Okay, so those are the reactions from this category that we started covering last time. Questions about this so far before we get into equilibrium? Yeah?
These reactions apply to all good nucleophiles?
Somewhat. It kind of depends on a couple of things. One is, I guess, like what we're going to look at, like the equilibrium actually affects it pretty strongly in terms of like whether this is even viable enough to be considered a reaction at all. So I don't remember if we get into halohydrin formation later on, but that would actually work pretty similarly, where instead of like C triple bond N, you might have a halogen here. But it turns out because that's a stable enough leaving group, the equilibrium really doesn't favor the product much, and so we don't really focus on it much as like a viable kind of reaction to use. So, okay. Other questions about that one? Okay, cool. So equilibrium in these reactions. There's actually a lot of useful information we can get out of where it lies for these molecules. Okay. So there's actually two different factors that turn out to control what's going on. So we're actually used to seeing these factors come up in different reactions in the past, but we're not used to weighing them against each other. Sterics is one of them, and electronics is another. So how bulky are things that you're trying to cram in together versus how much charge are you trying to stabilize? So we've actually seen kind of this like division in the past. Like SN2 is controlled almost exclusively by sterics. SN1 and E1 are mostly controlled by electronics because you're looking at stabilizing a positive charge. Now we're kind of looking at both in the same system. Okay, so sterics basically comes down to before the reaction you only have 3 groups around the central carbon. After the reaction you have 4 groups around the central carbon. So the sterics are understandably going to be a little bit tougher in the product. So basically the bulkier the groups on the central carbon are, the worse the product is going to be stability-wise, and the less the product is going to be favored. Okay. So I kind of have 4 different examples up here. One is if we're doing this on formaldehyde, and we try doing any one of these reversible additions, doesn't really matter which. I guess in the notes I have it showing a hydration, so let's go with that. Here, the sterics in the product are pretty negligible, so the product has no reason to be disfavored. If we start ramping it up a little bit and maybe put in a single methyl group on there, like this, then we're going to be about breaking even. I guess you might be wondering why I'm showing this favoring the product instead of having this one be even. I guess it ends up being the case that the second vector, electronics, actually favors this one too, but we'll get to that in a second. Okay, so for this one, again doing the same reaction. Here, the sterics are pretty much at the break-even point where it's not really a big deal, but there are still some sterics disfavoring the product. Once we go from an aldehyde to a ketone, though, it starts to be a big issue. So like if we do a couple methyl groups, now the product is really having some problems. And then if we actually start changing from methyl groups to, say, a T-butyl group, now the equilibrium pretty much entirely favors the starting material. Okay, so questions about that one? Okay, cool. So that's half of the deal. Okay, so the other factor in play here is electronics. And this really is controlled by how big is the delta positive on the carbon. In the carbonyl form. So smaller delta positive means more stable, means the starting material is actually a little bit more favored. Okay. So this doesn't just focus on how many R groups there are, but also on what type of R groups. So, and I guess this also follows the same rules that we're used to seeing from positive charge stabilization for, say, carbocations. More R groups there are, the better they are at stabilizing the positive charge, just like in, a more substituted carbocation. So here, in formaldehyde, these H's are pretty much useless at helping out. So this has a big delta positive, which means the starting material is pretty unstable relatively. And so that's another reason why for this formaldehyde here, it actually really favors going to the product so that it can get away from that uncomfortable delta positive charge at the carbonyl. Okay, so in other words, if we look at the same molecule under the 2 different factors that we're applying here, sterics and electronics are actually totally in agreement for this one. Sterics means that the product is good, and electronics means that the starting material is bad. So both of them are sort of helping to push the reaction all the way to the right, or really far to the right at least. Going up to an aldehyde. Here there's a little bit of assistance from the methyl group on one side, so it's sort of a medium delta positive. So equilibrium here is about break even. Once we bring in two R groups, one on either side, now the delta positive is actually small. And so this thing is not too badly off, and also we already know that Sterics are saying the product is not great. So again, Sterics and electronics are in agreement pretty much for all three of these. Like the cases where the big delta positive is on the starting material also happen to be the ones where the product is good, and vice versa. Okay, to introduce a fourth one here that's different from the fourth one over there, because T-butyl and methyl are pretty similar in terms of helping stabilize the delta positive. So looking at T-butyl here wouldn't really tell us much. But what if we start tweaking the type of R group that we have, and instead of H3C, what if we do F3C? Because to draw that out, if we do another CF3 group over here, if you remember, the inductive effect is pulling electron density out towards all three of the carbons here, all three of the fluorines here, away from the carbon, which means that this, instead of helping to stabilize a delta positive here, is actually wreaking havoc on its stability by putting even more delta positive on this carbon. So this one's going to be actually a huge delta positive. So this one is actually pretty unstable as a starting material, which means that here the equilibrium is actually strongly going to favor the product. Even though the Sterics is working against us, you know, it's two alkyl groups, it turns out that electronics here are so bad that in the competition between electronics and Sterics here, electronics ends up dominating, and so equilibrium favors the product, even if it's a little crowded looking. Okay. So one other thing that's worth pointing out, this is looking at the equilibrium constant. The rate for the reaction is usually more or less proportional, just because usually the electronics, the size of the delta positive kind of influences the rate of reaction. Like the smaller delta positives are less reactive, and that reaction will not only favor the product less, it'll also go slower. So okay. All right, so I guess the take-home message for this whole section is if you put an aldehyde or a ketone in water and there's any acid or base around, it's going to be doing this reaction in equilibrium whether you want it to or not. But it may not end up mattering because, say it's a ketone, it's only going to spend a small percent of its time in the diol form anyway. Most of the time it's just going to be looking like its normal ketone self. But with an aldehyde, especially with formaldehyde, if you put it in water and acid, it's actually going to spend most of its time in the diol form, or at least a significant amount of time. So I guess like formaldehyde, a lot of the time that's available as a water solution instead of just pure formaldehyde. And so really you're not getting a bottle of this stuff, you're getting a bottle of this diol form most of the time, just because unless you dehydrate it and pull all the water out of there, it's going to be spending most of its time as the diol. Okay, so questions about that? Yeah?
So does one trump the other when it comes to like using products?
Not universally. So really, I'm going to try to avoid asking questions where it's like a competing effects kind of deal, just because that's not really a fair question, and I would have to go look up the actual experimental results to know how it comes out anyway. So yeah, usually if I ask something, it'll be either like only one effect changes between them, say like maybe I swap out a CH3 for a T-butyl or something, and then Sterics is the only thing changing, or maybe I'm going from like 2 methyls to 2 trifluoromethyls, and then electronics is the only thing changing.
So is the delta positive decreased because there's a slight delta negative on the R group carbons?
Yeah, so kind of like what happens when they're attached to a straight up carbocation, like they're doing hyperconjugation to send a little bit of their charge density in towards it to sort of help carry the load of the positive charge, or even if it's only a delta positive. Okay, yeah.
So the sterics and electronics, those can be adaptable hydration.
Yeah, and really they can apply to every single thing in this chapter. It's just usually it's not as reversible a reaction, and so just because here, if we did the reverse reaction, we're kicking out a pretty decent stable leaving group, and some of the other reactions in this chapter, we're adding something that's never going to come back off, and so equilibrium doesn't matter too much because too bad it's on there permanently. So, yep. Okay, so other questions about this one before we move on to a new category? Okay, cool. Okay, so the next one we're going to look at is actually the reverse of a reaction we saw in OChem 1. So we're now looking at reductions to alcohols. Okay, so as kind of a reminder, we saw like the overall deal here when we were looking at like the roadmap for this chapter pretty much, but you take some kind of carbonyl having thing, aldehyde or ketone, and you reduce it and you're going to get the same thing, only instead of 2 bonds to oxygen, you now have an OH group and an H on there. Okay, so the way to think through the reagents that we need for this are really what we need is some source of H that's going to come in with a minus charge or partial minus charge, because we're sending H to attack on this delta positive carbon. If we try to stick a proton on here, that's obviously not going to be great. So we're going to add the equivalent of H minus onto that carbon. And then later on, the oxygen here can go pick up a proton on its own somewhere else. Okay, so the reagents that we're going to use, there's actually a bunch of them, but we're only covering 2 of like fairly different strengths. Really it comes down to like how strong is the negative or delta negative charge on the hydrogen, and how reactive is the, I guess, hydride donor that we're going to use. Okay, so the 2 that we're covering are sodium borohydride or Na plus BH4 minus, or it's just written as NaBH4 usually on the arrow. So the BH4 minus we actually saw a little bit of this thing way back in OChem 1 when we started covering Lewis dot diagrams and how to figure out like formal charges and stuff. But it pretty much looks like this. There's no lone pair on the boron. When this thing wants to ditch its negative charge, it has to do it by having the BH bond go out and attack something, for instance, a carbonyl. So that's one. The other one that we're going to cover is lithium aluminum hydride. Which is kind of the equivalent, Li plus and AlH4, or This one actually gets an abbreviation of LAH for short. And there, if you're ignoring the lithium counterion, it looks pretty much like that. All right, so given that boron is right above aluminum in the periodic table, aluminum is actually more electropositive, and so there's more of a negative charge on the hydrogens here. So this one does the attack in the same way. It's sending out a hydride because aluminum doesn't have any lone pairs to attack with. But this one has bigger delta negative on H and is more reactive. Okay. So in fact, lithium aluminum hydride is reactive enough that you cannot use it in a protic solvent. Kind of think of it as like sort of being like an organometallic. It's a really strong base. So if you try to use LAH in a protic solvent, all you're going to accomplish is, say you're throwing this thing in water because you don't remember not to do this, but basically all that's going to happen here is aluminum's hydride is going to come off immediately and just go pick up a proton from water, from whatever protic solvent that you have, and you're going to get, I think that's called alane, and then H2 gas, which is basically made from like H minus and H plus, or their equivalents sticking together, and then hydroxide. So this gas like just leaves the reaction immediately, and because of how much heat you generate doing this, you want to be real careful there's no sparks around because this is a good way to start a lab fire. So don't use LAH in the presence of anything protic. Not a good idea. But for sodium borohydride, it's unreactive enough that it does this reaction still, but a lot slower. So you can actually get away with using sodium borohydride in protic solvents. Okay, which is good because it turns out to be more convenient if you can use this reaction or do this reaction in a protic solvent, just because then you can do it all as one step instead of subsequent steps. Okay. Okay, so questions about this so far? All right, so the mechanism, there's actually two different versions that I've seen. I think I ended up switching to the one that the book uses now and also the one that's on sapling, which is the stepwise reaction. And I'm realizing I didn't update the paragraph that talks about maybe it's concerted instead. So I guess for the purposes of our homework, we're going to treat it as a stepwise reaction, but be aware that other people might show it as concerted. Okay. So the mechanism is we're starting with our carbonyl, aldehyde, or ketone, or whatever, and it's actually pretty much the same mechanism as what we've been looking at in the previous section. Something nucleophilic comes in and attacks the base of the carbonyl, and then later on the oxygen goes and picks up a proton from wherever it's available. So if you know that reaction from over here, you're already good on this section. It's just the nucleophile is a little bit more complicated looking because instead of just one piece that goes in and attacks, it's sort of detaching part of itself to go to the attack. So like any one of the BH bonds can go attack the base of the carbonyl. Then you get O minus, and now the hydride has added on there, which is how we've gotten the H onto the carbon that we needed. And because sodium borohydride, we're actually okay to do this in a protic solvent. At this point, we can just have whatever protic solvent we've got. Maybe say we're using methanol. I think when you guys do this in lab in a week or two, you'll actually be doing it in ethanol now, if I remember right. But it can go pick up a proton from whatever solvent. And that gives you the final products. Note also that we are, as a byproduct here, kicking out borane, BH3, which you might recognize from like hydroboration oxidation. But we're also making methoxide, OMe minus. And so these two are actually going to get together. So even though our molecule here is done, what's interesting about the byproducts is that we're actually sticking them together, which means that we now have, again, a boron with a minus charge and some H's on it. So this can actually go through the whole cycle again with another copy of the carbonyl, send another borane to go attack, and then be neutral for a little bit until another methoxide comes and attaches to it, and then it's negative again. And so basically, you can do this reaction a total of 4 times, one for each hydrogen that was on there to begin with. Okay, so this is actually a pretty efficient way to get reductions going. You only need 1/4 as much on a mole basis of NaBH4, and it'll still reduce every one of your carbonyl molecules in theory.
Are you going to get the ether forming from the methoxide attacking the carbonyl?
So you might get a little bit, I think, because this boron here with its empty orbital is actually a lot more reactive. Okay, so I guess like that's a very good question. We do see some reactions where methoxide goes for the carbonyl, but we'll cover that in a bit because there's a little bit more going on as well. Yeah, but generally I think if it does attack, it probably just like gets kicked back out reversibly afterwards, and sticking onto the boron ends up being like the longer term kind of thermodynamic sink for that. So, okay. Yeah.
Is there any difference in charge distribution as you move down the reaction into hydrogens? Like, does it slow down because of that?
Good question. I don't actually know. My guess would be, because oxygen's more electronegative than boron, my guess is, yeah, this minus charge is probably going to get a little bit smaller as you go through the reaction, which means that each one is probably going to be slower than the previous one. But I guess it ends up being favorable enough that if you throw in only 1/4 as much sodium borohydride, it still ends up going to completion. So maybe it slows down, but not enough that it ends up being impractical, I guess. So, yeah. Okay. So other questions about this one? Yeah, hi. No, unless I say like specifically like show this happening 4 times, which seems like kind of a waste of exam time, honestly, if you've shown it once already. Then yeah, you only have to show it happening for the one equivalent. So, Okay, so let me move the camera real quick. Okay, so the overall reaction for this is going to be written as carbonyl, and then you can just straight up write NaBH4 and MEOH. And because it's okay to have sodium borohydride and the alcohol in together, we don't have to do step 1, step 2. We can just throw it all in at once. Oh, that's another thing I was going to address is that it sounds like depending on who you had for OChem 1, some people are under the impression that just putting something above versus below the arrow is 2 separate steps. And I wanted to clear up the record that that's not actually the case. Unless we explicitly do like step 1, step 2, or A, B, whatever, it's all implied to be in there at once. So above and below the arrow or beside the arrow or like hovering around nearby has pretty much no bearing on anything. Like I could have written this the same as NaBH4 MeOH, and that means the same thing. Unless we specifically say stepwise, it's all assumed to be present at the same time. Okay. Okay. So for sodium borohydride, it's just a nice, easy kind of one-pot reaction. You just chuck it all in and it's done. But for lithium aluminum hydride, we got to keep it separate from our product source. And so this is going to be a little bit more fiddly. So you do the hydride first, then the proton. So, and there is actually something else that changes as a consequence of that too. Okay, so again, your hydride source goes in and attacks, kicks up onto the oxygen. Okay, and now it doesn't really have a convenient proton source to go pull an H off of. And so I guess you could show this with boron as well, but it's not as big a factor there. But here, because the molecule is just sitting around waiting forever while you don't have any protons available, this is actually going to sort of temporarily complex onto the aluminum, kind of like methoxide did over here, only it's the molecule itself like binding onto the aluminum in the meantime. So like that. Okay, and so again, it can do the reaction up to 4 times, but in the meantime, it's being stabilized not by a byproduct, but by the actual like unfinished product itself. And then eventually, we're going to do an acidic workup, kind of like we did for organometallic stuff in the past, to get rid of the minus charge on the product. And then this oxygen can split off the aluminum, go pick up a proton, and then that gets you to here. Okay, so overall, we would write this one as step 1, lithium aluminum hydride, and step 2, H3O plus. Okay. So yeah. So it's actually the sigma bond that breaks and goes to do it, which is why, like, it's sort of like the arrow pushing for when the hydride came off and went and did the attack. It's just the sigma bond is the highest occupied molecular orbital doing the attack. So, Okay. So yeah, the big difference between these two, as far as we're concerned for now, is that one's concerted, or like one's sort of a one-pot reaction, and the other has to be 2 separate steps, like the reaction then the workup. So long as we're looking at aldehydes and ketones, that's pretty much the only difference between them, but it turns out there's actually bigger differences that are going to start popping up once we start looking at different types of carbonyl compounds in the next chapter or two. Okay. So basically think of sodium borohydride as like the weaker version, and lithium aluminum hydride is the much stronger version. Uh-huh.
Wouldn't that arrow indicate that aluminum is actually grabbing the hydrogen?
Not necessarily. I guess kind of like here where the sigma bond breaks and it's actually the hydrogen that goes and does it. Here it's the sigma bond that breaks and it's the oxygen that goes and does it. So it's kind of an equivalent to this step. And I guess if you didn't know anything about the nature of the two atoms attached, like you could, or I guess like you would have a hard time predicting which one's going to end up doing it, but it also helps to keep in mind that out of the two atoms here, the oxygen is more electronegative, so if one of them steals the electrons out of this bond and goes spends them somewhere else, it's probably going to be the more electronegative one, if that makes sense. Kind of like hydrogen did over there. Uh-huh.
What other solvents could we see with the NADH4?
Yeah, so alcohol solvents are like the traditional way of doing it, so like MEOH or ETOH, and really it could be any alcohol, but those are like the cheapest and easiest to deal with, so that's kind of what we use. No, but I'm not sure. Oh, I bet I know why. It might just be a solubility thing, like the ketone or aldehyde kind of doesn't dissolve in it as well. Yeah, so. Okay. So other questions about that one? Okay, cool. So then one last reaction in this category that's totally different from all these ones, but is actually like really similar to something different that we've seen before. And that is, if you remember alkene hydrogenation, you can actually sort of do that with a CO double bond instead of a CC double bond. So again, you need to add a hydrogen to one atom of the double bond and to the other atom of the double bond. So at least like functionally, this turns out to be pretty much equivalent to what you're doing to a to what you're doing to an alkene, only it's on a carbonyl. But the big difference is in an alkene, it's like a non-polar bond. Both the ends are pretty much equivalent. Here, it's a polar bond, and so it turns out that the catalysts that you need to use, palladium and platinum, for whatever reason, don't work as well. So nickel actually turns out to be a little bit better. All right, so take your carbonyl and you hit it with H2 and nickel, and you are going to hydrogenate that bond. The huge downside to this is that even though we don't normally use nickel for alkenes, turns out it'll go after alkenes just fine. So if you're trying to just go for the carbonyl in your molecule, but you've got an alkene there, too bad, hydrogenation is going to mess up both of them. So if we wanted to reduce this carbonyl, but without touching the alkene, that's where we'd fall back onto sodium borohydride or lithium aluminum hydride.
Does this work with the aromatic that had a carbonyl in it?
Depending on how much you pressurize it, because if you remember to get rid of the aromatic ring, you got to just heat and pressurize it.
The aromatic, you just do low temp and pressure.
Heat the carbonyl, you mean, or?
Well, if you want to hydrogenate the carbonyl, you want to keep it aromatic ring.
Oh, I see. Yeah, yeah. So if you wanted to do that, you could selectively. So here, let me draw what you're asking about so other people can see. So like, say you have this guy. This one you could actually get away with H2 and nickel at like room temperature and pressure. and you would just get the carbonyl getting messed with. But then like if you did the same thing, like high temperature and pressure, then it would probably go for both eventually. But yeah, this is a good one where like the reactivity is pretty different between these two, and so just depending on like how much you beat it over the head with these conditions, you can pick how much it reacts. Okay. Any other questions about this category? That's a pretty good place to wrap up. Okay, cool.
Question about that one. So the product still